Bismillahirrahmanirrahim. Assalamu alaikum. Here we are talking about unit number 11, which is the last unit of our syllabus. Here, and we will talk about the wastewater treatment in detail. So, as we discussed in the last unit also, and before that, unit number 8 also, about the wastewater treatment, how the different stages of the wastewater treatments are there, the primary treatment, secondary treatment, tertiary treatment, and different type of the units and unit operation and unit processes like the bar rake screen, grid tank, sedimentation tank, aeration tank, clarifier, disinfection units. All this we discuss in that one. Here, let us see in these units one by one. For example, the bar rake screen. Bar rake screen is a structure like this one, where the bars are placed, and when the wastewater pass through these bars, the big solids can be removed from here. So this is the first step of the treatment. And generally, why we do this one, to protect the piping system, the wastewater treatment plant and the pumps. Maybe this solid, well, it will go to the pipes and the pumps, it may damage that. So the coarse bar rake screen could be there like this one, and the spacing between them could be around 3 inch and or 75 millimeter. And it is could be a manual one, or it could be a mechanical one like this one. It can rotate with the pump, with the motor, and it can be stationary. You can clean manually, or you can clean by some mechanism. Like here, when it will move, the solid will fall, and another chamber where it will be solid will be collected. So it could be yani this traveling rack screen. It could be placed maybe after that, or it can alone can be provided with the treatment plant. So this is the traveling bar screen, this is the normal bar screen, stationary bar screens. When we design the bar screen, there are a few things we should remember in our mind, like the design criteria, the standards. The approaching channel should be straight. Approaching channel mean the wastewater, when it is coming towards the bar rake, this it should be straight. If it is curved, something like that, then the flow of the water will reduce, right? So and this channel length at least should be 0.6 meter before the screen, right? So it will provide a uniform flow through the bar. And the approaching velocity should be at least 1.5 feet per second, or 0.46 meter per second. Yani the velocity should not be less than this, otherwise the solid will settle in front of the bar rakes, right? So the coming velocity, the velocity of the water which is before the bar rake, it should be more than that. And velocity through the bars, it should be less than 2 feet per second, or 0.62 meter per second, right? This is the design flow criteria. And velocity through the bar should not be more than 3 feet per second, right? It should be between these two values. It should not be less than 2 feet per second, and it should not be more than 3 feet per second. These are the design criteria. When we design the spacing and the diameter of the pipe, then bars, we decide that based on these values. And this bar rake, when the water pass through the bar rake, there will be some energy loss. The water is coming with some velocity. When it is passing through the bars, it will reduce with the velocity, the energy will reduce. So this loss in the energy, which is called the head loss, can be calculated by this equation. So you can use this equation to calculate how much will be the head loss in your design channel. So here VA and VB is the VA is the approaching velocity, yani before the bar, the water coming, and VB is the velocity through the bar, through the opening. So yani between the bar, when the water will pass through the bar, because the area will reduce, the velocity will increase. So VB minus VA, that's why it is here. And G is the acceleration due to gravity. And by this equation, you can calculate how much is the head loss between the bars. Let us see in this example to understand this use of this formula. When a mechanical bar screen is to be used in an approaching channel with a maximum velocity of 1 meter per second. Approaching velocity is 1 meter per second, yani VA is 1 meter per second. The bars are 15 millimeter thick, and the openings are 25 millimeter wide, right? The dimension is giving. Determine the velocity between the bars, yani you have to calculate the VB, and the head loss, yani the from the previous equation, head loss you have to calculate. So once you will calculate the VB, VA is already given to you, you can find out HL. So in order to solve this equation, uh, the diameter of the bar is given to us, right? This is 15 millimeter, and the spacing between the bar is also given to us, 25 millimeter. These are the bars and this is the spacing. If you consider unit area of the bar rake screen, maybe assume that the this is the width W and this is the depth D. If it is W and if it is D, we are assuming that one. So the net area of the screen, the total area of the screen is this W into D, right? Will be equals to W into D, and if we multiply with this ratio, if we want to know how much is the area of the opening, we can multiply with this ratio, yani 25 over total width, yani this is 25 divided by this total width, then we can find out the area of the opening. So in the within total area, how much is the opening, I can find out with this relationship. Okay, in normal area, as I told you, this is W into D, right? So the before the bar, the area is without bars, so the area of this section will be W into D, and between the bar the area is this one. So if I apply the continuity equation before the bar and between the bar, VA is the approaching velocity, area A is the area of the this section, which is W into D without bar, and VB is the velocity between the bars which we want to calculate, and AB is the area between the bars opening. This is this one, right? So if I will put all this value, this WD will cancel out, I will get the VB. So I got the velocity between the bars. I have already the VA, which is 1, VB is 1.6. I can calculate now the head loss. So if I put this value in this equation, I get the head loss 0.114 meter. So this is the use of that formula, which we can use for designing of the bar rake screen. Grid, grid chamber is a unit operation where we remove the grit. Grit is, as I told you, the small solids like the sand, grit, stone, broken glass. These are the particle like this one, which can be removed from the wastewater. So why we do this? Because we in order to protect the pumping system and the piping system, because it may damage the pumps, right, and other equipment when it will go to the further in the piping system. So that's we can do in the grit removals chamber, which is a normal unit where we remove these solids. Biological process is the aeration tank. The aeration tank is a place when we put all the water, the wastewater in a big tank, and we provide the mixing of the air. Purpose of the mixing the air to add the oxygen in the wastewater. More oxygen we will add, the bacteria will grow and they will eat the waste material, and they will remove the waste material from the wastewater. Water will become clean. So there are two types of the biological treatment processes. One is called the suspended growth process and another attached growth process. In the suspended growth process, everything is in suspension in a big tank in the water. In the attached growth process, we grow the bacteria on some solid material like the stone and other thing, and then we pass the wastewater through that to treat that. So generally the design of a this biological process needs some information: what type of the microorganism present in the wastewater, uh, what are the different type of the reaction take place in the reactor, what are the effect of the environmental parameter like temperature, effect of the temperature, effect of the dissolved oxygen, how much the waste material microorganism can remove, reaction kinetics of the microorganism, yani how fast microorganism can work. For example, in the low temperature region in Canada and other places where the temperature is low, the wastewater treatment is slow. But in the region like our region, the temperature generally is high, the treatment is very fast. So the most common process used in the domestic wastewater treatment is the activated sludge process. Activated sludge process is a suspended growth process, which is the most common process in the Kingdom of Saudi Arabia. More than 90% of the wastewater treatment plant are designed based on activated sludge system. This is the suspended growth process, activated sludge system, where the wastewater is in suspension. Everything is there in suspension in a big tank, and you are mixing with the fan with the air, so more oxygen will be added. So treatment will be going on, and the water is coming from these channels. So this is suspended growth process. Activated sludge process, I told you, is the most common one. So little bit about the activated sludge process. The basic activated sludge process actually need the microorganism to do the treatment. So, and in any wastewater, generally in the domestic wastewater, there are a lot of bacteria present. So you can keep them in the water in the suspension and provide the aeration. Then the reaction can take place, right? And once you will do this in the aeration tank, after that you put in the sedimentation tank, so you can remove the solids, the bacteria from the wastewater. You will get the clean water. And if you want to recycle this bacteria again into the system to speed up the reaction, then there could be a recycling system for returning the solids which are removed from the liquid solid separation unit in the like the sedimentation tank and back to the reactor. So the reaction will be continue, the treatment will continue, and the wastewater will be treated constantly. The important feature of the activity process is that they in this aeration tank there will be flocks will be formed, and these flocks are actually made up of the bacteria which are settleable solid that can be removed by gravity settling in the sedimentation tank. So this is the important feature of the activated sludge system. Active stress system generally use the microorganism, bacteria is needed, and mixed growth of the microorganism. Yani there are variety of the microorganism, normal bacteria we need, and aerobic condition. Yani we need air all the time. So oxygen actually help these microorganisms to grow and do the treatment. Microorganisms and some definition just I will go over. Microorganisms are those bacteria and the other microorganism which can be helpful for the treatment of the waste material by using the wastewater as a substrate and as a food. They use the waste material as a food, and they remove this organic material by microbiological respiration. Yani they take the oxygen for respiration, and they do the they take the waste material as the food and they synthesize, they produce new bacteria, right? Mixed liquid suspended solid, what is this one? This is the amount of the bacteria and the waste material in per unit liter, per unit volume of the wastewater is called as the MLSS. So you can see that generally in the aeration tank, the quantity of this mixture is 2000 to 4000 milligram per liter. So this is mixed liquid suspended solid. There is another type of the mixed liquid volatile solids also there, and generally it is 80 to 90% of the MLSS. So most of the solid mass in the wastewater is the MLVSS. There are different type of the flows coming to the aeration tank. Feed water, yani the water which is coming. Waste activity sludge, yani after the treatment there is some from the bottom some solid sludge will be removed. Recycled activity sludge, yani maybe you will recycle back some microorganism in the tank again to speed up the reaction. So these different type of the flows are there in the aeration tank. This picture will clarify that one. The active cell system consists of aeration tank and the sedimentation tank. This is the complete active cell system. So there is some wastewater is coming, having some bacteria, some food, and in this we provide mixing with the fan, or maybe injecting the air by some diffuser. So there will be more oxygen, the bacteria will be there, and the waste material there. After some time the waste will be converted to the bacterial cell, then we'll pump this material to the sedimentation tank. Here all the solid including the bacteria or remaining solid will settle down, and we will get the clean water. Maybe some solid you will waste as a sludge, you will throw it, and some you maybe you will return back because there are some microorganism and you need more microorganism to treat this wastewater, so some you recycle. This is the active sludge system. This is some the values about the activated sludge system. There are different type of the activated sludge system. Tank rectangular could be there, it could be a circular one also. So these are some of the standard criteria. So just to give you the idea, effect of temperature is there on the rate of the reaction, yani how fast bacteria will remove the waste material from the wastewater. So the rate of the reaction, the K, it depending on the temperature, and if the temperature increase, the rate of the reaction will increase, the bacteria will work fast. So if you have, for example, the rate of reaction at one time, it, you know that you can find out the rate of reaction at any other time by this relationship. It is called as the Arrhenius relationship. This we have already seen in unit number 3 also, Arrhenius relationship. So this equation, for example, the value of the theta is constant, right? It is a constant, it is known. So if you, for example, at 20 degrees centigrade, you know the K1. So in this equation you can put the at any temperature like 50 degrees centigrade, what will be the K, so you will get the K2. So this equation can be helpful for calculating the any reaction rate at any temperature. This is one of the example, detailed example. This is a little bit in detail. We can discuss this later on if you want to go over that. It is not within the scope of your syllabus, but I just put as an example for you about the design of this treatment plant. Attached growth process, like the suspended growth process, this is another type of the wastewater treatment plant, in which what we do, we use like the stones and the plastic material, any solid material, we grow the bacteria on that. Once we grow the bacteria on that, we put this in a big tank and we spray the wastewater over that. We spray the wastewater, it is moving like a circle, like a clock, this arm, and there is a wastewater spraying. When the wastewater pass through this solids at the bottom, it will become clean, because all the waste material will be taken by the bacteria which are grown in this stone, in this media. They will take the waste material. When the water will reach to the bottom, it will be clean. So this is attached growth process. It is one of the process in which microorganisms are attached to any inert packing material like the stones and the plastic or any other material. This packing material could be the rock, slag, redwood, many things, right? And it operates as aerobic and aerobic process. Here not only air is needed everywhere. In some stage places, like when it will go, what wastewater go inside, maybe some less oxygen will be there, so it will be anaerobic also. So it will operate in aerobic and aerobic process. Packing material can be submerged completely, and you can fill up to the top with the wastewater, or maybe just spray. So most common process is the trickling filter. Like in the remember, like in the suspended growth process, the most common process is activated sludge system. In the attached growth process, the most common process is the trickling filter, right? So in the same way, in this process there is a sedimentation tank. Like in the activated sludge system, after the aeration tank there is a sedimentation tank. Here also, after the activated after the attached growth this unit, right? In this one there is a sedimentation tank, right? Where we remove the bacteria, remaining bacteria from the wastewater. Trickling filter, as I told you, it is a biological process in which the microorganisms are attached to the filter media, like in the stone and other thing. Trickling filter are having the component like the influent pipe, rotary distribution, yani that pipe which is circulating and spraying the wastewater. Filter bed is there at the bottom. There is a filter bed under drain system, yani from where the wastewater is coming from the that trickling filter tank, and effluent pipe from where the wastewater is coming out. At the downstream we put the sedimentation tank, yani after that we put one more tank which is sedimentation tank to remove the remaining microorganism bacteria from the wastewater. The medium what we use, as I told you, the stone, gravel, slag, plastic, redwood, many material we can use. This is a section of the trickling filter. This is the actual picture. It is filled with the media, and this is the rotary distribution system which is spraying when it is moving in circle. So the wastewater is spraying on the top, and once it will pass through that, it will come to under drain system, then it will be removed from the this effluent pipe. So from the effluent pipe it will be taken the influent pipe, bringing the wastewater here and then spraying at the top. So this is the cross section of the trickling filter. Cracking filter classified basically based on two criteria. Trickling filter classified into the low rate or intermediate rate, high rate, super rate, and based on the Q. If it is treating high Q, it is super rate. If it is treating very low Q, yani flow rate, then it's a low rate. So according to the Q, we can classify. We can classify according to the organic loading, yani how dirty wastewater it can treat, liquid loading, yani how much the wastewater you can pass through the trickling filter, and recycling implied or not. Maybe you have a recycling system in the treatment plant or not. So based on that you can also classify. So these are the two type of the classification which can be done in the trickling filter. This is the picture of the single stage. For example, this is the wastewater coming from the primary treatment, then it will be going to the trickling filter. After trickling filter it will go to the sedimentation tank. This is one unit, so this is a single stage. If you add one more unit, with this one add one more unit, then it is called as the two stage. If you add more and more, it will become the different stages, multi-stage trickling filter. Depending on how much treatment you want to do, you can add the units based on that quality of the effluent you need. When you do the treatment in the trickling filter, there are some problems when we use that one. Sometimes the floating sludge may be formed on the surface. It will choke the surface. So if for example in this tank, if the sludge will accumulate, sludge mean any solids, then it will choke the filter. This is one of the problem. Fly may be grown on the filter because it is open to the air. The maybe the fly will grow on that, and it will cause the nuisance in the area, and also the odor problem. So you cannot build a trickling filter near the ascan and the people where people are living, because it may produce the lot of the odor problem. So these are the some operation problem for the trickling filter. There is one more type of the treatment is there, which is called as the RBCs, rotating biological contactors. These are the drum type of the thing in which we grow the bacteria, like this one. This is wastewater, and these are the drums, and bacteria grown on this drums. So when the drum is rotating, like this one, the drum is rotating. It is when it is going inside, the bacteria on this surface which take the waste material, wastewater is passing through here, and when it will come here, they will take the oxygen from the air and the bacteria, and then again bacteria will go here and take the waste material, taking the air, taking the waste material, like this it is continue. So these RBCs are very famous also for the wastewater treatment. Generally you can put multiple disc shaft drums, and you can add more disc to increase the size of the treatment plant, right? And generally the wastewater flow perpendicular to the shaft, as I shown you here. This is the shaft which is inside the paper, and this is the perpendicular flow of the wastewater is there. And about 40% of the total disk area generally is inside the water, it is submerged. And biological film growth on the disk, yani bacteria will grow on the disk. As the shaft rotate, the biological film soak organic material from the wastewater, yani when the waste this shaft will rotate, the bacteria will go inside and they will take the waste material, organic waste material from the wastewater. Oxygen is absorbed from the air to keep the aerobic condition. As I told you, when it will go to the open air, it will take the oxygen. Multi-stage RBCs are used generally to remove more BOD, right? And the slot bacteria mean which are washed with the wastewater from the disk. It can be removed in the clarifier, and in the next tank where you can put a sedimentation tank. No recycling is implied in this type of the treatment. Biological activities are reduced during cold weather. So if it is a cold weather area, the efficiency of the treatment is low, like in the Canada and other places they are not using RBCs. But if the climate in the cold climate these RBCs are there, you have to cover to avoid the heat loss, so then the bacteria will work, otherwise the efficiency will become very low. The last one is the stabilization pond. Stabilization pond are like a open the ditch or the hole in the ground. You can dig the hole and you can fill with the wastewater. So what will happen in this one, actually, when you fill with the wastewater, there is oxygen from the surface, right? Oxygen will go inside. There are some bacteria. The bacteria will take the organic material, they take the oxygen, and they will settle down in the bottom, right? And from the top, after maybe some time, you can remove that. So the sunlight help to grow the algae also. The algae may grow on the surface, and this algae, when it will in the sunlight, it will produce oxygen. Oxygen will be taken by the bacteria, so the bacteria will take this oxygen and they will produce more bacteria, carbon dioxide, and ammonia, which is needed for the food. Then again the algae will grow, the oxygen will go to the bacteria, so a continuous process is there, right? So this is the stabilization pond. In the stabilization pond, remember, stabilization pond, also known as oxidation pond or the lagoons. These are the other name for this one, and it is the very old ancient wastewater treatment process known to the human being. And generally in the rural area, in the villages, we find this type of the treatment because it's very cheap, because it doesn't need any special any treatment method, and you need a big area which is generally available in the villages. And these ponds generally around a depth of a meter and a half meter deep, okay, and size depending on the quantity of the wastewater you are treating. And generally we use the algae, bacteria, and other microorganism which can remove the waste material from the wastewater, and it can treat the wastewater. The requirement for this kind of the lagoons is there. These stabilization ponds are simple to construct because you have to just dig this. A bulldozer is used to remove the soil from the ground and create a basin in which water can be collected. The first requirement of the sewage pond is that it must be surrounded by a berm. You should provide a border here, so the maybe the rainwater cannot go inside, right? It will also prevent like the animals, other thing, to go inside, right? So this berm is very important. This also at the bottom we should provide the like the clay or some lining, so this wastewater cannot leak into the groundwater, so it cannot cause the pollution in the groundwater. When we want to design the this pond, stabilization pond, this equation we can utilize. The volume of this pond can be designed, find out by using this equation, where C is a coefficient, right? And that for in the FPS system, this is the value of the C, and in the SI unit, this is the value of the C, and the Q is the flow rate, and the S is the influent BOD, and how much the waste material is there. So BOD or COD value will also be given to you. So you will know the Q, you will know the S, and C is a constant factor. Theta is actually also a temperature coefficient, which is having the constant value. In the next slide I will show you that value. And T at the temperature at which you are working, and in which area you are having this stabilization point, so that temperature of that area. F and F dash are toxicity factor or sulfate, chemical oxygen demand factor. Generally for the industrial or municipal wastewater and most of the industrial wastewater, these are factors having the value of 1. So in our designing we can keep F and F dash as 1. So this formula helpful for us to find out the volume of the this tank required to treat the wastewater. As an example, for example, if I want to find out the volume of the stabilization pond, let me decide the depth before doing this calculation. And theta is a constant, as I told you, 1.085. I put theta here, right? And the depth I keep constant, 5 feet. right? So then I will just calculate the area, because depth already I know. The C is a coefficient. I can use this coefficient based on any system of the unit. S is the BOD value. This will be given to us, right? And the F dash and F is 1, right? And at any temperature I can put this temperature, I will get the area in meter square for the stabilization point. So these two formulas to calculate the volume or calculate the area can be utilized to design the facultative pond or the stabilization pond, right? So this is all about this unit. If you have any question, just let me know, we can discuss that, right? Inshallah. Thank you very much.